Now, in the last section, I would like to talk about multiple linear regression. Now, this is optional. It's a little bit more of an advanced topic, but for me personally, I like it, and I wanted to just kind of introduce you very quickly to it and go through an example. So, a multiple linear regression is a way to model the linear relationship between one quantitative response variable. So, let's jump in and try to define that better. So to repeat, in a linear regression involving two or more variables, the response variable is the variable being modeled or predicted, while the predictor variables are the variables used to predict the response. As you can see here on your screen, for a model with more than one predictor variable, the population multiple linear regression function is, now here's a nice equation for you, right? E of y equals beta naught plus beta 1 times x1 plus beta 2 times x2 plus beta 3 times x3 all the way to beta n x of n plus epsilon, where beta naught, beta 1, beta 2, beta 3 are regression parameters, and epsilon is the regression error term. We've seen this before. So now what better way to illustrate this than going through an example? So I'm going to use a data set about wine quality. Now here's a link that I'm going to click on. All right. Just to show you exactly, again, it's https archive.ics.uci.edu/ml/datasets and then wine plus quality. Now, this is from the machine learning repository, and it's a wine quality dataset. So if you wanted to look at the dataset when it comes to white wines and red wines, get some more information, you can visit this website, click on the data folder, see here, and then download the CSV files. Now, of course, as a citation request, this dataset is public, available for research. The details are described in Cortez et al. 2009. Please include this citation if you plan to use this database. So, all right, I had to put that out there. So again, this is about wine quality, and this was created using red and white wine samples. The inputs include objective tests, pH values, and the output is based on sensory data, median of at least 3 evaluations made by wine experts. Now, each expert graded the wine quality between 0, which was very bad, and 10, very excellent. So as you can see here, we have number of instances, red wine 1600, 1599, white wine 4898. And there are 11 attributes when it comes to output attributes. So over here, the input variables, you have the fixed acidity, volatile acidity, citric acid, residual sugar, chlorides, total sulfur dioxide, density, pH, sulfates, alcohol, and then the output variable, and then of course quality, which is a score between 0 and 10. All right. So really quick, if you download this dataset, I'm going to now be looking at winequalityred.csv. So first things first. First, I want to import my modules and then read the CSV file and load in a data frame. So I went ahead and copied and pasted some code to read the CSV file and then create a data frame called red wine df and then take a look at the first 5 records or so. All right. So as you can see here, these are the attributes that we were talking about earlier: fixed acidity, volatile acidity, pH, sulfates, alcohol, and quality. Now, if we go back to the website, they do reference this really actually great paper, and it's called Modeling Wine Preferences by Data Mining from Physiochemical Properties. And it's great. They actually propose a data mining approach to predict human wine tasting preferences that is based on easily available analytical tests at the certification step. So it's a good read if you go to the website and try to access it. But what I want to jump in and talk a little bit more about is first we're going to do some data stats, which now you've become experts at. But I'm going to show you one of the tables that they were looking at when writing their paper. Where over here, the attribute, fixed acidity, all the way to alcohol, and then the red wine, and then they have the minimum, the maximum, the mean. Now, if you recall a few lectures back, we were talking about measures of center, measures of variability, and of course the 5-number summary. So we're going to try to create a table that looks like this with one line of code. I'm excited. All right, so if you recall, our data frame is called red wine DF. All we have to do now is just type describe. Now, if you forgot what describe function means, it's going to generate a 5-number summary. If you recall, 5-number summary, you have the 25th percentile, the median, the 75th percentile, the mean, the standard deviation, the minimum, and the maximum. All right, just to repeat again, minimum, maximum values, Q1, the median, Q3, those form a set of descriptive stats called the 5-number summary. Now I'm going to alter this slightly. So what I'm going to go ahead and do is transpose. And I only care about the minimum, the maximum, and the mean. So what I'm going to go ahead and do is type over here, min, max, the mean. All right. Awesome. Now we're going to go ahead and do a quick check over here. 4.6, 4.6, 15.9, 15.9, 8.3, 8.32. Nice. Volatile acidity, 0.12, 1.58, which is about 1.6 to 1 decimal place, 0.52, 0.5. Isn't this fantastic? Now I'm going to apply one quick trick here. I'm going to type PD option display float format. Instead of over here, you can see there's 1, 2, 3, 4, 5, a lot of decimal places. I am going to try to reduce that to 3. So PD options display float format, and run it again. This makes it a little bit easier on myself to read these values. As you can see, 4.600. Wonderful. Our numbers, our values match the values from the paper when it comes to the data stats per wine type. All right. Next step, what I would like to do is to create a 12 by 12 correlation matrix. I want to see how all these attributes are correlated with one another. So again, I'm going to write one line of code over here. I'm going to just say my new data frame, I'm going to call it, let's see here, AX, and then we said this data frame is called red wine DF. So here's a nice trick. Instead of typing every single variable in there, I'm going to go ahead and create my 12 by 12. All right. So now going to shift things around a little bit. Ha! Here we go. Now you can see how all these attributes are correlated with one another. Now I want to apply one other trick. I'm just going to try to sort these columns by quality. All right. So what this is going to do now is sort the values based in an ascending order by quality, by their numeric value. And as you can see here, we're starting from negative 0.258 all the way to 0.124. Makes it easier for me to say, okay, well, quality, my highest value over here when it comes to correlation is alcohol. There's a moderate correlation here, which is 0.5. So that is the strength of the correlation. It's positive, and then on the flip side of the argument, there is a negative 0.4, when it comes to the volatile acidity and quality. So this is a negative correlation. This is a positive correlation. So again, a negative correlation between the two variables. It means that as one variable increases, the other decreases. And then on the flip side, when it comes to the positive correlation between the two variables, it means that when one variable increases, the other variable increases as well. Beautiful. So now what I would like to do also is I want to create a bar plot of my 12 by 12 correlation matrix, and I'm going to try to create a bar plot of attribute versus quality correlation. So I'm going to go ahead and copy and paste some code. So again, I just imported Seaborn as far as a module, created my new data frame, set my figure size, set up my style. I want to drop quality as an attribute because it doesn't make sense if it's a value of 1 over here. I'm going to sort it, and then I'm going to plot it. And as you can see here, this is exactly what we're talking about as far as negative correlation and positive correlation. You can see over here, this is a moderate strength when it comes to the correlation. The alcohol, which is volume as a percent, and then volatile acidity. Now what you see over here matches almost perfectly with the results, conclusions, and implications of the paper, whereby it states that an increase in alcohol tends to result in a higher quality of wine, as you can see here. The citric acid and residual sugar levels are very important, where the equilibrium between the freshness and sweet taste is most appreciated. And last but not least, the volatile acidity has a negative impact, since acetic acid is the key ingredient in vinegar. Now, they also mention in the paper, when it comes to sulfates, the most intriguing result is that the high importance of sulfates might be related to the fermenting nutrition, which is very important to improve the wine aroma. So again, this lines up pretty nicely with their findings. But again, I highly encourage you to read that paper and then go through the code and try to come up with a 12 by 12 correlation matrix and create the bar plot. Now let's take it one more step and try to plot this as far as our data frame. But in this case, I would like to create a 3D scatter plot. I'm going to use the mplot 3D toolkit from Matplotlib, which will allow us to plot 3D objects such as scatter plots. And I'm going to be taking a look at alcohol, sulfates, and quality. So again, my two predictor variables are going to be my sulfates and alcohol. And I'm going to try to visualize this in 3 dimensions. So I'm going to copy and paste some code. Import the modules, use the same data frame, now called df. I'm going to define my x, y, and z, create my scatter plot, look at it from specific angles, and then label my x, y, and z. I'm going to try to run that, and beautiful. I was able to create a 3D scatter plot output, which is shown. And it shows how a multiple linear regression model with true predictor variables can be visualized in 3 dimensions. Beautiful. And again, to repeat, my predictor variables are my sulfates, alcohol, and my response variable, quality. So again, if you want to change the views, you go over here and play around with this following function, view_init, and control the elevation and azimuth of the axes. Excellent. Now for fun, I wanted to explore further the relationship between these variables. So I went ahead and created a scatter plot matrix, which is a collection of scatter plots organized in a grid. So as you can see, I created a grid of my variables here, alcohol, sulfates, and volatility. And what you can see here when it comes to the diagonal is my univariate distribution plots to show the marginal distribution of my alcohol data, my sulfates data, and my volatile acidity data. And it confirms that when it comes to the relationships between alcohol, sulfates, and quality, there is a positive correlation, and you can see here the values in green, or even a little bit darker, which is the blue, and that indicates the higher quality rating. And on the flip side, when it comes to the negative correlation of quality and volatile acidity, as you can see here, that's flipped, where the lower the value is when it comes to the volatile acidity, the better or higher quality wine rating it received. So a scatter plot gives the relationship between the two variables, and we'll cover that in future lectures on how to create a scatter plot matrix. So what I'm going to go ahead and do is, now the next step is I'm going to try to determine the residual standard error and coefficient of multiple determination. And just to repeat, my response variable is quality, and my two predictor variables will be alcohol and sulfates. Now, if you recall from the previous lectures, we can determine those by creating a ordinary least squares regression from the module statsmodels.formula.api. So let's go ahead and figure it out. So I'm going to copy and paste some code here. Again, you've seen this before for simple linear regression. My predictor variable's quality. Now the only difference here, we have one other predictor variable. In this case, we have alcohol and sulfates. So all you have to do is join the predictor variables by including a plus sign. That's it. Other than that, everything is going to be identical. And voila, here we go. We have our coefficient of determination, r squared. We have the standard error, which is the estimate of the coefficient. We have the p-value. We have skewness, kurtosis. So again, skewness is typically the measure of symmetry of the data about the mean. Kurtosis is a measure of the shape of that distribution. And of course, there's a lot of other measures that are included in the regression results. Now let's dig in a little deeper and use analysis of variance to test the correlation between the two variables. In this case, alcohol and sulfates. These are the predictor variables. Now, if you recall, the OLS function took the quality as a response variable and alcohol and sulfates as the predictor variables. So the next part is we're going to use the sm.stats.ANOVA_LM function that takes in a linear model and outputs an ANOVA table. All we have to do is type print sm.stats.ANOVA_linear model, and then model, comma, type equals 2. Of course, before we run this, let's import and run. Outstanding. Now, finally, we have all the information that we need to determine SSR, which is overall sum of squares, the overall regression mean, MSR, the F statistic and the p-value, and of course, the residual standard error. All right, let's delve in. Now, the most important question is, what is our sample multiple linear regression function? And if you forgot what that meant, if we scroll up, we are trying to determine the multiple linear regression function in this format. Now, all what we have to do is simply type model dot params, and right away we're able to determine the parameter estimators to our linear regression function. Our intercept is 1.375, and my regression parameters for alcohol, x1, is 0.346, and my other regression parameter for x2, beta 2, is 0.994. So again, if you recall, at the top, my regression parameter, beta 1 and beta 2, in this case, beta 1 was for alcohol, which was 0.346, and beta 2 was for sulfates, which was 0.994. And my intercept was 1.375. Outstanding. Now, as I was scrolling, I did notice I created my ANOVA table incorrectly. This should not be an E, but TYP equals 2. Just wanted to point that out because this value over here is going to go from 1596 to 760. All right, just typo on my end there. Outstanding. So my linear regression function y hat equals 0.346, which is the regression parameter for alcohol, plus 0.994 regression parameter for sulfates, plus 0.1375, which is my intercept, which, as you can see, also you can find from the OLS regression results, which are right over here. Outstanding. Now, one would ask, well, what is my coefficient of multiple determination? R squared. Well, you can find it right here, 0.27, 27%. That is the proportion of the total variation in quality, which is accounted by the linear regression model with alcohol and sulfates as the predictors. Or, if you do not want to find it in the OLS regression results, then all you got to do is type model.r squared, 26.99%. Outstanding. So again, r squared measures the proportion of total variation in y that is accounted for by the linear regression model. Now, my overall regression mean square is typically my sum of squares divided by p minus 1, which in this case is 2. So quite easily, if I wanted to just determine my overall regression mean square, then all I gotta do is type model.msc underscore model 140. Now for folks that would like to delve in more, my MSR is the SSR divided by P minus 1, and then my MSR divided by MSE, which is the residual mean square, will give you the F statistic. Now my residual mean square, my MSE, right, is very important to determine the residual standard error. How can we figure that out? Well, all you gotta do is type model dot MSE underscore RESID. And of course, just type model. And finally, from that value, if we take the square root, then we can find our residual standard error. So what I'm going to go ahead and do is copy and paste some code that we've used in the past. So again, I'm just taking the square root. And finally, my residual standard error was determined to be 0.69. So again, just to reiterate, the residual standard error in multiple linear regression is the square root of the residual mean square. Now, to summarize, the smaller that value, the better the predictive performance of the model is. A relatively small residual standard error indicates that the actual future value of y is likely to be relatively close to that predicted value. Therefore, just to summarize again and to simplify, the less residual standard error, the better. Now, these again are hard topics, but we were able to determine the correlation between different variables. We were able to plot 3D objects and show how a multiple linear regression model with two predictor variables can be visualized in 3 dimensions. We were able to produce a ordinary least squares regression results, determine the residual standard error and coefficient of multiple determination. Outstanding. So just a quick review and retrospective. Regression is an amazing topic and it really segues very well into our next module. Now just to summarize, with regression, you're able to predict a value of a continuous valued variable based on values from other variables, right? And in some instances, it assumes a linear, or in other instances, a nonlinear model of dependency. Regression is studied in statistics and econometrics, and there's a broad range of applications from predicting sales amounts of new product based on expenditure, or geared more towards a scientific viewpoint, right? Like predicting the wind velocities as a function of humidity or air temperature or air pressure. And last but not least, time series prediction of stock market indices with auto-regressive models. Now in this section we were talking about multiple regression. With multiple regression we can forecast a variable of interest using a linear combination of past values of the variable. And a lot of people are interested in using autoregressive modeling, and especially with machine learning for stock market prediction and trading. Because investors, they raise profit from stock markets by maximizing the gains and minimizing the losses. Now, the stock market is very volatile. So that's where predictive modeling comes into play because it allows the investors to make these informed decisions. And how do you accomplish that? By using forecasting models. And then you select the best one in order to develop a profitable trading strategy. So this is a very important topic, but very exciting.